Swayam Prabha. Digital India. Educated India.
Okay, welcome back. And in this module, we were discussing the two-body scattering problem, the scattering of the alpha particle with the gold nucleus problem, where we have used the fact that the gold nucleus is no longer fixed and it's a two-body problem, right? So then we were trying to find the scattering angle and the recoil angle. So we see that, let us say the scattering angle is theta 1 and the recoil angle is theta 2, and we see that tan theta 1 is 4 q1 q2 p times e divided by 4 pe square minus 1 minus gamma square q1 square q2 square. Okay, and then we have that tan theta 2 is 2 pe by q1 q2 1 plus gamma. Okay, so where our E is the original or the initial energy of the system given by half m1 u square, which is just the kinetic energy of the alpha particle, and our gamma is the ratio of masses m1 by m2. So we can look at the simple case where equal masses are concerned. So for equal masses, we have gamma is 1, and in that case our formula is reduced to this simple form: tan theta 1 is q1 q2 by pe, and tan theta 2 is minus pe by q1 q2. If we want to find theta 1 plus theta 2, we can use the tan theta 1 plus theta 2 formula, and we can quickly deduce that theta 1 plus theta 2 is 90 degrees, which is what we expect for lastic, at least for lastic collisions, right? So here we can see that tan theta 1 plus theta 2 is going to give us infinity, or theta 1 plus theta 2 is 90 degrees. Okay, so this is certainly the case for equal masses and lastic collisions, right? So we are not, again, we are only looking at the setup in the Newtonian frame, no relativistic frame. Okay, so then we talk about the two-body scattering cross-section next. So what we are talking about next is two-body scattering cross-section. So again we use p theta 1 relation. We use p theta 1 relation for the two-body problem, right? And we see that sigma two-body problem, sigma theta 1 is minus p by sine theta 1 dp d theta 1, right? So this is our two-body problem, and typically this is this particular derivative dp d theta 1 is quite complicated. It has a complicated expression. So we simplify our formula as follows. So what we do is, notice that dp d theta 1 using chain rule can be written in the zero momentum frame as dp d psi times d psi d theta 1 being the scattering angle, and then this is going to be so using this chain rule, we see that sigma TB, sigma 2 body, is nothing but sine psi by sine theta 1 times d psi d theta 1 times minus p by sine psi Here I have again used another set of ratio here, and times dp d psi, right? So we see that this particular formula shows us that this sigma 2 body is also sine of psi by sine of theta 1 times d psi d theta 1 times sigma zm psi. Okay, and let us call this expression as 1 because we will be using it later, and we see that we can write from this two body problem, we can write this two body setup in the zero momentum frame by replacing our mass m1 by the reduced mass, and theta by the scattering angle psi. So we can find sigma zm from sigma 2 body problem, from the sigma 2 body, by replacing our mass m1 by the reduced mass, and theta, the scattering angle in the two body problem, by the scattering angle in the zero momentum frame. And when we do that, we are going to further, well, what we are trying to do is, all these replacements can be done, but there is one more derivative which remains, d psi d theta 1, that we need to find. So we need to find psi as a function of theta 1. So this is something we need to find, right? So we see that what have we got? So to find psi as a function of theta 1, we see that this is sine of psi minus theta 1 can be written as gamma times sine theta 1, and so from here I can invert this relation. This, let me call this relation as star. I can invert this, and I see that psi is theta 1 plus sine inverse gamma of sine theta 1, right? And we see that d psi d theta 1 is 1 plus gamma cos theta 1 by square root 1 minus gamma square sine square theta 1, right? So we have differentiated this new relation, this inverted relation. Let me call this as 2, right? So we can directly deduce that from 1 and 2, I can find my sigma 2 body theta 1, the scattering cross sectional area for the two body problem in terms of the scattering angle theta 1. Earlier it was with respect to the total angle theta. So so for the Rutherford's problem, let us now come to the zero momentum frame. So what we have is, in the zero momentum frame, sigma zm of psi this time is going to be q1 q2 by 2m1 times u to the power 4 times 1 plus gamma square times sine of psi by 2 to the power 4. And then I can write from our previous expression 2, I can see that the two body scattering problem sigma tb theta is coming out to be q1 square q2 square by 16e square 4 1 plus gamma square times gamma cos theta 1 plus s, where s is another expression of theta 1, times s 1 plus gamma sine square theta 1 minus s cos theta 1, okay, whole square. So we have used in this complicated expression, we have used the binomial expansion. Here we have this square root hanging around in equation 2, so we have used binomial expansion, and where our expression s comes out to be, well, we are going to use it soon. So s is the binomial expansion will be used soon. So S is 1 minus gamma square sine square theta 1, and our energy E is half m1 u square. So we see that when gamma is much less than 1, so gamma is on one end, it's m1 by m2. So when it is much less than 1, and sigma TB is q1 q2 by 16e whole square, we have 1 minus sine to the power 4 theta 1 by 2 minus 2 gamma square plus some higher order expansions of gamma, which we are going to neglect in this particular assumption where gamma is a small value. Okay, so then typically if you go back, for example, in the Rutherford's experiment, so in Rutherford's experiment, gamma was found out to be of the value roughly 0.02, and in that case the error in Rutherford's experiment, if we use this formula, the error that was found in this two body cross section density was roughly 0.01%. So, so this simple looking formula was able to find the cross sectional density of the two body problem with surprising accuracy, right? So, with very less error. So, then we can also look at the case, the simplest case, when the bodies have equal masses, right? So, for equal masses, we have gamma is 1 and psi is 2 theta 1, and we see that d psi d theta 1 is coming out to be 2. So then with all this simple expression, we can quickly write down the two body cross section density, sigma TB theta 1 to be q1 square q2 square by e square times cos theta 1 by sine 4 theta 1, and we see that theta 1 comes out to be between 0 to pi by 2, right? And this is typically, let me call this formula number 3. So typically 3 applies to particles of equal nature. For example, the scattering of protons by protons, right? So so that's the scenario. So for example, scattering of protons by protons, proton scattering. Okay. So then how about the case of multi-particle system? So what to do with multi-particle system? We need to simplify our diagrams and simplify our setup so as to write the force balance for a multi-particle system. So we resort to the so-called velocity diagram. What exactly is velocity diagram? So we are tackling now multi-particle system. Multi-particle system. Okay. So this question is, how does one find velocities and angular velocities of elements of S, right? And when two or more more generalized coordinates, we are talking now of a multi-particle system, so we go back to our discussion using generalized coordinates. So when two or more generalized coordinates vary simultaneously. Okay, so as I just promised, we will resort to the so-called velocity diagram. Velocity diagram. Okay, so we draw. So what are the steps? So let me write down the step by step setup here. So what we do is, the first step is we draw the diagram. We draw the system in the most general possible setup at any given time point. So we draw the system in general position. When I say general position, I mean at any given time point, and select the generalized coordinates. Select the generalized coordinates. Okay, and then we let the first generalized coordinates vary, right? So let the first generalized coordinates vary, and we see that we keep other generalized coordinates fixed. Keeping other coordinates fixed, right? So the idea is, we try and write up the force balance for one coordinate by keeping all the others fixed, and repeat it for all the other coordinates, and then we combine all these setup through linear superposition. So what we have is, so keeping all the other coordinates fixed, and mark the velocity of each element. Okay, and then we repeat it for all the other coordinates. Repeat for all other coordinates, generalized coordinate, I mean. Okay, so then, as I just said, when all the coordinates, they vary simultaneously, that is what is happening in the real life, right? So when all coordinates vary simultaneously, the velocity of each element of S is the vector sum of the velocities of that element. Okay. Okay. So when the coordinates vary individually, so that's the setup, individually. Okay. So then what we have is, let us look at these set of steps for drawing the velocity diagram through an example. So the example that I have is something we have discussed in one of our previous modules, that is a particle which is tied to another particle with a string of constant length and allowed to move in a constraint. So we have two particles P1 and P2 be connected with light inextensible strings of length A, right? And the particles P1 is also constrained to move along a fixed horizontal rail. And the system moves in the vertical plane. So the idea is, well, let me complete this statement and then we can explain. So, and the system moves vertically. Okay, so the problem says we have to find, draw the velocity diagram, and of course identify the generalized coordinates. So we are going to take, so the setup is we have one particle which is allowed to slide horizontally, and it is connected to another particle P2. So P1 and P2, and the whole setup is allowed to move vertically. So in this setup, we can, since it is allowed to move vertically, we can assume that the string remains taut, or the string remains, string doesn't remain, go slack, and in that case, the length of the string is given to be A, and the second particle is then allowed to only move in the angular direction when the system moves vertically. So then, which means that we can take the horizontal displacement of the first particle and the angular displacement of the second particle, x comma theta, to be our generalized coordinates. Right? And we see that if that is the case, this is x dot, and then if the first particle is moving horizontally, then the second particle is also moving horizontally, because the first and the second are tied up, and also the second particle is also moving, showing an angular velocity, right? So we expect that there is also another velocity of the second particle along the tangential direction, which is given by a theta dot. So here with this geometry, we see that this is theta. Okay, so then, so let us follow the step by step of drawing the velocity diagram. So step one is, we have, let us say we fix the zero of the frame, and at any given time point we have particle 1 which is allowed to move horizontally, and the particle 2 which is connected to particle 1, and since the system moves vertically, we have an angular velocity of the particle 2 as well, and of course the length of the string is A, and that is what we have, right? So let us say at any given time point the displacement is x. So this is our system at any given point of time, the most general setup. And then we can also, we are going to vary our generalized coordinates. So vary x and theta, where this is x and theta being fixed, and we see that x and theta is given by P2, and this is P1, and this is x1. Well, x dot being the horizontal displacement, horizontal velocity of the first particle, and of course the second particle is also moving horizontally with the same horizontal velocity, and the finally our step. So this is our step 1, step 2. So step 2 was we vary x and theta, right? So vary x and theta being fixed. So theta is fixed, we are varying x. And then now the third step of our velocity diagram is we are going to vary theta, but we are going to fix x. And we see that in this case we have P1 times P2. We see that this is A times theta dot, right? And we have that this is what we have. Okay. So vary theta and fix x. Okay. So, and then finally the step 4 of the velocity diagram is we are going to arrive at the final velocity diagram, where we overlap or we superpose all the motions that we saw in step 2 and 3, and we get the velocity diagram, which is as follows, right? We have the horizontal motion of particle P1 as well as the angular motion as well, and the horizontal motion of particle P2. So we have superposed all the different components of the velocities. Okay, so that's the most general velocity diagram. So how to solve such problems? So let us see. So the problem is in the form of an example. So let P1 P2 uh, be as in previous example. So I'm not going to draw the velocity diagram. So it's all understood here. We are talking about the previous setup, right? And they have masses 3m and m, and the rail is smooth. So which means that there is no friction on the rail, and the system moves under uniform gravity. Under uniform gravity. And initially the system is released from rest. The system is released from rest. Okay, and with the string making an angle of 60 degrees. With the string making an angle of pi by 3, right? And with the downward vertical, with respect to the vertical. Okay, and then we have to find the equation of motion of the system using the various conservation principles. So use conservation principles. See, so far we have looked at conservation of momentum and conservation of energy. So use conservation principles to find equation of motion. So we don't want to use, the problem says don't use Newton's laws of motion, but use the energy and momentum conservation. So then see, we have to, let me quickly draw the diagram so that we can label the various components and look at the conservation. So we have P1 here. So let us call that P1 is moving along the x direction. So we call this x direction to be I hat. Our convention is I hat is this direction, and k hat is the upward vertical, right? So P1 is this, and we have that we have well, of course, P2 is going to be this following, and P2 is also moving with x dot and moving with an angular velocity a theta dot. Okay, so what we have is that we don't have any external force on the system, so the system is isolated, which means that we can immediately apply the linear momentum conservation. So the linear momentum is conserved, and which means that we have the initial momentum of the system is 3m times x dot plus m times x dot is, this is the momentum of the second particle, so second, and this is the momentum of the first particle. So so m times x dot plus a theta times cos theta. So where did we get this? We have this as theta and a theta times cos theta. So this is well, so this is our a, and a theta times cos theta is going to be this displacement. So we have that this is the momentum at any given point of time, and so what we get is that this is 4m x dot plus m a theta dot cos theta, and this is going to be the initial momentum, which is P initial, and we see that this is also equal to 0. So P initial is 0, and we see that what do we get? So P initial is 0 because both the particles are at rest, right? So both particles at rest. Okay. We also see that the constraint, see, in all this setup, we understand that the constraint forces do no work on the system, because the constraint forces, for example, the normal reaction on the particle P1 by the floor is going to be perpendicular to the motion of the particle. So when we take a dot product of the force with the velocity is along the perpendicular direction, we are going to get zero work done. So the constraint forces do no work, since they being perpendicular to the motion, right? So since constraint forces do no work, we have that energy is going to be conserved as well. Energy is conserved. Why? Because we have been careful by explicitly mentioning the rail is smooth. Smooth means that there is no friction, there is no dissipation of energy from the floor, and we can apply the energy conservation. If we do that, our kinetic energy of the system is going to be T is given by half times 3m times x dot square, so that is for the heavier mass, and plus half m times x dot square plus a theta dot square, a theta dot whole square, plus 2x dot a theta dot cos theta, right? And we see that what have we done? We have used the triangle inequality, that v being the total velocity, so v square is mod of v1 plus v2 square, which is mod of v1 square plus mod of v2 square plus 2 times v1 dot with v2 cos theta, theta being the angle between the two velocities. Okay, and then we can also write the potential energy of the system. Let us say that the first particle, which is moving horizontally, is at zero potential, or the base is held at first particle. So the second particle is at a downward distance of a cos theta. So we have the net potential energy will be, for the first particle it is 0, for the second particle it is going to be mg a cos theta. And if we add up these two, we see that that's going to be the total energy. E is going to be Ke plus Pe. And then we will have, so that's the total energy, and we can quickly write down the total energy. The total energy comes out to be the kinetic energy plus the potential energy. So 4 times x dot square plus a square theta dot square, plus 2a x dot theta dot cos theta, minus mg a cos theta, that's the potential energy, and that is going to be the net energy of the system, the total energy, which can be found at the value given at t equal to 0. We see that the bodies are at rest and they're making an angle of 60 degrees given by the problem, and this is going to be minus half mga. So cos theta is half. So that's it. So then, so this is our energy conservation here, this giant expression, and we see that from here we can quickly write down the final expression. So we have noticed that we had two variables, so let me call this as equation number 2, and the momentum conservation that we wrote down was equation number 1, right? So remember, now we have two conservation principles, two equations describing two unknowns, or the two generalized coordinates x and theta, and that's what the problem was asking, to find us the equation of motion, right? So we stop here, and in the next module we will look at another example. We will continue our discussion on the same example. So thanks so far for listening.